Hello, my name is Rami Ben-Ari. I'm from Origin AI, a newly established research center in Israel. I'm going to present TAEN, Temporal Aware Embedding Network for Few-Shot Action Recognition. This is a joint work with Mor Spiegel-Naxon, who was an intern while I was at IBM Research and currently at Technion, and Ophir Azoulay, Udi Barzilai, and Daniel Rothman from IBM Research AI. I'll start this presentation with a short introduction. I then present the motivation for this work, then continue in describing our suggested model, which is a network. I'll talk about the loss function components and our evaluation method based on Kinetics 400 and ActivityNet 1.2 dataset. I'll wrap up with a short summary and conclusions. Action recognition is one of the first tasks in video analysis where the machine is aimed to recognize certain actions occurred in a video. Applications include event detection, clip classification, and retrieval in multimedia storage, or to name a few. Deep learning methods are data hungry and require a large set of tagged datasets for each new category, which makes these methods often impractical. New categories can be rare and data tagging expensive, particularly when videos are considered. In few-shot learning, one can learn to classify new categories by seeing only a small set of examples, known as shots. Although action recognition was handled in computer vision for decades, few studies address the challenge of few-shot learning in this domain. In this work, we present a new approach that takes into account the long-term connectivity between different action parts in order to improve interclass dissimilarity between action categories. The elementary task in action recognition is looking at a short, trimmed video that contain a certain unique action and classify those videos into their associated category, such as washing laundry, wood chopping, or brush stroke, as shown here. An extension of this task includes temporal action detection, where the model sees a long untrimmed video and where the target is to detect the timestamps or temporal boundaries of all predefined action categories. Here, the model needs to deal with background segments of the video and tackle with a strong imbalance between foreground and background video sections. Let's now look at a high level on our method before diving into the details. At first, we chop each video into 8 segments. Each segment then describes part of an action that we call sub-action. An embedding function then maps each sub-action to a feature space encoding both appearance and motion cues. These sub-action embeddings are arranged by the temporal order, introducing a trajectory in the feature space to be used as the action representation. We associate each class of action with a trajectory prototype. At test time, a new video is mapped to a trajectory and classified according to the distances between the trajectories in the embedding space. Our target is to learn the sub-action prototypes and trajectories that allow optimal discrimination between different action categories based on a few examples. In this slide, we see our architecture for learning the action trajectories. At top, we initialize our prototype learning scheme by a constant inserted in a fully connected layer. The output of the fully connected layer is a vector of size, number of classes by number of sub-actions by the prototype feature dimension. This represents all sub-actions of all action categories concatenated. At the bottom branch, we derived a representation for each sub-action by applying a pre-trained network and average pooling. The embedding is then learned via a series of fully connected layers. 3 loss functions ensure that the trajectories are well separated. Note that both branches are jointly optimized, introducing a joint optimization of prototypes and the embedding functions. In this work, we have 3 types of loss functions enforcing a prior on the generated embedding manifold. The first and most obvious one is the affiliation loss. This loss enforces the sample sub-action embedding to be close to their corresponding prototype sub-actions. The second loss is the motion loss. This loss drives the motion vectors between 2 consecutive action segments to be similar, as shown in the figure. And the last loss applied on the prototype trajectory is the diversity loss, separating between sub-actions and avoiding the collapse of all trajectory points to a single point. The idea behind this loss is that well-separated and longer trajectories are more discriminative. In the few-shot scenario, our goal is to train a network that generalizes well to new action classes. In this setup, we are given a training set that consists of labeled videos from different classes. This set is denoted as the base set and is only used during training. Base classes may include washing laundry, wood chopping, or brush strokes as shown before. For testing, we use a small number of videos from new classes such as fixing a bike or washing dishes. These classes were not present in the base set. Our task is video classification in trimmed video or temporal action detection in untrimmed videos. Number of classes in the support set is called N ways, and the number of examples for each category in the support set is K shots. For the classification task, we follow the experimental setup in previous works using the same backbone feature extractor C3D pre-trained on Sports 1 million. For the temporal action detection, we pre-train our I3D backbone only on the base set of ActivityNet 1.2 to avoid any chance of feature contamination. We follow the evaluation protocol as previous works. We compare our method to a baseline and three previous methods, CMN, TAEN, and TAM. We observe that the accuracy grows with the number of shots as expected. As our baseline, we use the C3D feature space without our embedding, which represents the classification accuracy where each video is represented by a single C3D feature using max pooling. Without our metric learning, C3D shows inferior results. Our model also outperforms previous methods of CMN and TAEN while being inferior with respect to TAM that uses temporal alignment based on dynamic time warping with a cost of O(n)² complexity. Generally, the results from our method present a growing gap for higher number of shots with respect to previous methods of CMN and TAEN. This shows that adding more samples yields smoother and more reliable trajectories. In this section, we illustrate an extension of our model to the temporal few-shot action detection task. To this end, we use temporal region proposal network called boundary matching network. Setting a probability map, the region proposals are then processed to reject the remaining background segments and classify the foreground clips to their corresponding action class in the support set. We test our model on the ActivityNet 1.2. For more details, please refer to the paper. The detection performance is measured via the standard mean average precision, MAP. The results show that TAEN can provide high results also for the temporal detection task. While we achieve comparable performance to SMN in one shot, we outperform SMN in 5 shots by a large margin. In the paper, we also provide several ablation studies. Here we can see the variation of accuracy with respect to sub-action granularity and number of shots. We observe that 3 to 5 sub-actions are sufficient to capture the action structure and enable improved recognition. Note the gap with respect to raw C3D features in one shot. In this work, I presented a novel deep network that learns to present actions as trajectories in the feature space, expressing connectivities between action parts. Our network jointly learns the action trajectory prototypes and the embedding function. We further extend our model to few-shot action detection in untrimmed videos, showing the performance on both tasks. Tested on 2 tasks of video classification and temporal detection, we show comparable results to state-of-the-art. A recent study shows that using the sub-action alignment improves the result with the cost of O(n)² complexity. Thanks for watching.